I'd start the show off right with a movie from one of my simulations that I've run recently on Mira with very little explanation. So I study core collapse supernovae, which is the death of a massive star. And the problem is these things don't like to blow up. That's our challenge, is getting them to blow up. But three-dimensional computing of this phenomena is cutting-edge stuff, and we're just starting to be able to do this. So this is a three-dimensional volume rendering from one of my recent simulations of core collapse supernovae. The shock is the blue bounded surface. You see all of this neutrino heated convection going on behind that shock, and that purple ball down in the center is the nascent neutron star, where the densities exceed nuclear densities, and it's cooling via neutrino radiation. And so this is, with not too much explanation, this is what I work on in terms of extreme scale computing. And my weapon of choice for this is, as Rusty mentioned, the Flash multiphysics simulation framework. And Flash does all kinds of different problems, not just astrophysics problems, laboratory problems, turbulent nuclear burning problems, a wide array of things. It's a multiphysics code, it's modular, it's been well designed, it's professionally designed by not astrophysicists, but by software engineers. It's open source, it's very easy and extensible to use. It's been applied to many different problems across many different application domains, and it's really a great piece of software. It got me through my PhD, and it got me a job, and it got me a fellowship, and I have a fondness for this code. So if you want to talk more about that, we can talk a lot about Flash, and I should just say that I'm going to touch on a lot of different things in my slides, and I'm not going to go too deep on anything, but if you guys want more depth, raise your hand, ask questions, interrupt me, stop me. We can talk about anything you want. You don't have to hold your questions to the end, and we can dive down deeper on the things that interest you guys. A little more on Flash and the things that relate specifically to my problem. Flash is solving the Eulerian equations of hydrodynamics on an adaptive mesh refinement grid. It includes self-gravity via a solution of Poisson's equation, which is an elliptic equation. My problem uses a realistic tabular equation of state to provide the closure. And I have a neutrino leakage scheme, which is how I calculate the neutrino radiation emerging from the neutron star. So if many of you are probably already familiar with adaptive mesh refinement techniques. So the elliptical term, in this case, for Poisson's equation, we solve it by a multipole approximation because the gravitational potential in this case is roughly spherical, so it's well represented by an expansion in multipole terms. And so using that, we can calculate the potential rather easily and very efficiently. Flash also includes many different schemes for solving an elliptic equation, including multigrid techniques and FFT-based multigrid techniques. So it has a lot of different ways to approach a Poisson's-like equation, not just for gravity, but anything that can be cast as an elliptic Poisson equation. So in this case, realistic means it includes contributions from the radiation. It includes contributions from the electrons and positrons, which are degenerate and relativistic. And it includes contributions from the baryons, which experience a very extreme phase shift at high density, where once they reach nuclear density, the strong nuclear force becomes repulsive. And the effective gamma goes to almost a value of 3, which is extremely stiff. And that's actually what launches the shock that you saw in the previous movie initially, is that phase transition of the baryonic matter from sort of ideal gas to nuclear matter. So that's what I mean by realistic. So there's a lot of physics that goes into just the calculation of the equation of state in my simulations. From a code standpoint, what's important is that it's tabular. It sends an input of composition, density, and temperature to the unit that handles the equation of state. That unit spits back out the thermodynamics. And it happens to be coming from a table in this case. And that table is what includes all of this realistic physics. That's an area of research by itself. It's hard to test neutron star matter in the laboratory. We haven't quite got there yet, but we're working on it. So some of you are probably familiar with AMR, but this is just a pseudo-color entropy slice from one of my three-dimensional calculations. And I just want to demonstrate, this is the AMR patchwork that we're using. Each of these squares represents a cube that's, I think, 16 zones on a side. And so this is what the AMR hierarchy sort of looks like. You take away the background, and each color represents a different AMR level. So we're putting the refinement where we need it and not where we can't afford it. with Flash. And Flash can also do a uniform grid calculation. You don't have to use AMR with Flash. It's much faster, actually, if you do just a uniform grid calculation. But the AMR is what Flash was built around, is using the adaptive mesh refinement to solve tough multi-scale problems. And it's fairly efficient. There's more overhead the more layers of refinement that you add. But in Flash, with paramesh in particular, we use an octree, which you could probably tell by looking at this, right? This is not the sort of AMR patchwork that you see from the sort of Colella and Glasenberger and Colella AMR schemes. Being an octree allows us to kind of simplify the calculation a little bit, where we don't have to compute the higher levels. We only have to compute the lowest level. So adding extra layers of refinement isn't as overhead intensive as other approaches. And Flash scales very well. So this is scaling data from Mira that I recently put in for my Insight proposal. And this is my application, which includes magnetohydrodynamics, self-gravity, the neutrino leakage scheme, adaptive mesh refinement, and I/O. And this is going up to 32,000 nodes of Mira, right? And we use full parallelism, which is 4 threads per core and 16 cores per node. So that's 2.1 million threads of execution in that last dot there. And it's not perfect, but we shouldn't expect it to be perfect. But I'd say that's pretty good. So Flash scales pretty well. Of course, I/O is a pain, but I/O is always a pain. So for the longest time, yes, this is threaded. Okay, so 8 threads per rank. So I use 8 MPI ranks per Mira node and 8 OpenMP threads per MPI rank. So this is representing the threading as well. So that's my code. Very brief introduction to my problem. Very brief introduction to the main tool I use. And a little background about my experience with high-performance computing, and in particular code development with Flash. I've been working on Flash for a long time now, but I started as a wet behind the ears grad student where I couldn't do code development in a realistic way. I was just an astrophysicist. So I took Flash and I did a problem that required very minimal changes to the code, right? That's where I started. I think that's probably where most of us start, is you take an application package and you try to do what you need to do with as little change as possible, basically setting up new problems and tweaking the existing physics and the existing capabilities in the code. And then later on, as I got more comfortable with it, then I was able to add some new physics. But mostly this new capabilities that I added at this stage were based off of existing capabilities in the code. I would take something, I would say, well, I can change that to do what I wanted to do, and I would use that as a template. And then as I got more and more comfortable with this code and with computing and high-performance computing and programming these types of problems, then I was able to add completely new physics, such as the neutrino leakage scheme, that weren't based on existing code at all, that were all new code. And now I've been at Flash for a long time, and I've gotten more involved in the sort of core guts of the code, as well as algorithm development, different approaches for gravity, and solving it with that multipole approximation. I've threaded a bunch of the code because my application relies so heavily on threading in order to perform well. And this has been in the span of a short period of time, really, that I've had to learn all this. And it's been a steep learning curve. And a lot of these things don't come easy. And you're not necessarily taught in grad school these things, at least not where I went to grad school. And so this is, just to impress the point that it's been a rapid expansion of my use of extreme scale computing. This is twiddle numbers of my core usage for my project in the last few years. As a grad student, I think maybe I burned 500,000 core hours during my entire graduate school tenure, right? And that's working mostly on 2D problems, running them on hundreds of cores, maybe hundreds of cores. And that was at the University of Texas, and I used mostly resources there at the Texas Advanced Computing Center. And then I moved to Chicago, and I got access to bigger machines, and I was able to do harder problems. And then maybe I was burning 5 million, core hours in 2011. And then I was able to get access to my own discretionary allocations on Intrepid, and burned 12 million, something like that. And this year, I'm on track to burn 30 million on Mira. So it's been a quick evolution, and maybe 2014 will go up there, maybe. So it's been a lot of fun, but it's also been a very steep learning curve, like I said already. And it's not been necessarily easy breaking into the extreme scale computing, so to say. Early on, it's pretty easy to get access to medium-scale resources like what they have at NERSC or TAC, anything on the NSF TeraGrid. You can get a couple 100,000 core hours. That's pretty readily available. But for me, I really got access to big-time resources when I moved to Chicago and started working with the Flash Center and got hooked up with the folks here at Argonne and the machines here at Argonne. And now I have my own discretionary allocations, and maybe next year I'll have my own insight allocation. And the thing about discretionary time, it's what I've been using for the past couple of years. And so it's not just for code development and testing. You can do real science with discretionary time. Sometimes you have to scale back the scope of what you want to do, but a few million core hours is quite a bit of computation, really. And so do science with it. And if you can do science with your discretionary time, you make it easy for the director to justify giving you more, right? So on that note, give back to your patrons. The folks at Argonne and wherever you're getting your core hours, they're supporting your research and your science, free of charge. And providing these scale of resources, it's not cheap, and funding is not easy, as I think we probably all know. So help them justify their continued funding to their funders. Give back. Publish papers, obviously. That's what we all have to do. We all have to publish papers, and all Argonne asks of us is we put the little acknowledgement at the end of our paper that, hey, I used Argonne resources. Great, awesome. But there's lots of other ways that you can give back to the computing center where you're getting resources. If you have a really great viz, tell somebody. Tell Chell. She's right back there. She loves it. She will get it hooked up. It'll wind up in the brochures like some of my stuff has. If you give a press conference, let them know. Right? Say, hey, I wouldn't be able to do these kinds of things without the resources provided by ALCF or wherever you're getting your time from. So, give back. It's a good thing. And it endears you to them as well, which is a good thing. And do things like, give talks at training programs. Okay, so a little bit more about my science. We'll get back to that movie. I'll play it one more time. But now I'm going to make you pay for it by listening to me talk about my science. So I work on core collapse supernovae, and this is a tough problem. We've had it for 50, 60 years, the idea that massive stars blew up because neutrino radiation from the forming neutron star drove an explosion. That idea has been around since 1963, I think. All right? But the thing is, in realistic calculations, it always seems to fail. Certainly in 1D, it always fails. Now, we found in 2D that sometimes it works. Multidimensional effects like convection and something called the standing accretion shock instability, which is a fundamental hydrodynamic instability of the shock, aided the explosion. And so some models blew up. But they blew up with much less energy than what we know supernovae have. So they're observed to have about 10 to the 51 erg of energy. That's a big number. But it's only 1% of the original binding energy of the core of these massive stars, 1%. And almost all of that energy comes out as neutrinos. So we only need to trap 1% of the neutrino energy in order to drive robust core collapse supernova explosions. But the thing is, neutrinos are neutrinos. We've got billions of them passing through us right now from the sun, right? They don't interact. In fact, someone computed this, worked this out, it wasn't me, that integrated over your lifetime, you should experience a neutrino interaction once every 72 years, roughly like that, where a neutrino will actually interact with your body. So it doesn't happen very frequently. Weak interactions are weak interactions, right? Very small cross sections. So it's hard to trap that 1% of the energy. But sometimes it worked in 2D. Wasn't very robust, but some folks thought, well, maybe going to 3D is the answer. If 2D is marginal, maybe 3D is key. And we know that nature is three-dimensional. So these things have to blow up in 3D. So is 3D the key to these robust explosions? Is there some unknown, fundamentally three-dimensional physical parameter that's gonna help? And the first simulations done in this were very, very highly parameterized. The neutrino physics is the toughest part of this problem. Resolution-wise, this isn't really hard in terms of resolution, but the neutrino radiation hydrodynamics is really tough. So what we did was use very simple parametric calculations where it was just a neutrino luminosity emerging from the core that was set by hand. And you turn that thing down as low as you can go and still get an explosion out of these things in 3D. And what the group in Princeton found is that, indeed, 3D helps. These things blow up quicker in 3D than they do in 2D. It's easier to get an explosion in 3D than in 2D. The thing is, this wasn't corroborated by the German group who tried to do the same thing. They didn't wind up doing exactly the same thing, and they used much coarser resolution, which the Princeton group pointed out as being a possible flaw in their their design. So I thought, well, I could do this. I can set Flash up to run this problem. I can chug out a few three-dimensional simulations and compare them to 2D. And what I found was the opposite. 3D was actually harder to blow up in my calculations than 2D was. And this was startling. At first I didn't believe it. I thought I'd done something wrong. And I checked and rechecked. I reran calculations. I reran simulations until I was sure that this is the result I was getting. Whether or not this is how nature works, I don't know. And so this was puzzling. But in the end, I think that it's right. I think that this is the right answer. And the way to look at it is not that 3D is harder to blow up than 2D, but 2D, for some very fundamental reasons, is artificially easy to explode. So here's more movies. So these are just entropy slices now. On the left is 3D, and on the right is 2D. Everything else in these simulations is equal between each other. So we'll just compare the dynamics. And this, again, is entropy. And in 2D, what we see is this very characteristic of everybody's simulation in 2D, sloshing up and down the axis, right? This is an artificially imposed axis in 2D. It's cylindrical geometry. Stars aren't cylindrical. I don't know if you knew that. But they're not cylindrical. And this artificial axis, I think, is a big problem. Because when these things blow up, they blow up along the axis. There's no place else for it to go. In 3D, there's no such preferred direction unless you rotate the thing, which these are not rotating. So there's no such preferred direction in 3D. And when an explosion develops, it picks an axis. Wherever it becomes the most unstable first is the direction it blows up. And in 2D, you get this sort of bipolar looking. All right, so why then does 2D explode easier than 3D? Well, this is what we're looking at. If you were to take that 2D image and revolve it into 3D, that's what you're looking at. You get rings. Each one of those little curls is not the sort of natural convection that we would expect to see in 3D, which is on the left. It's a ring. Those rings are fundamentally unstable in 3D, which is why they don't exist in the 3D picture. And they're artificially more buoyant than a ring that gets broken up. It goes like the ratio of the surface area to the volume, because it's a drag versus energy absorption problem. In addition, turbulence plays an important role in here, right? Convective turbulence. And turbulence in 2D, many people in this audience can probably tell us, wrong. It's wrong, right? And one of the chief things that's wrong about it is the inverse energy cascade, which pumps kinetic turbulent energy to large scales. Well, the shock is a large-scale phenomenon. You put energy on large scales, it helps push the shock outward. In 3D, the energy gets cascaded to small scales, where it drives this very small distributed turbulence. So I think these very hand-wavy but pretty physically motivated reasons are why we should expect 2D to be artificially easy to explode. And what I've done since then is to increase the detail of the physics that I'm using for neutrinos, as well as gravity, and increase the resolution of my calculations. So this is a much more sophisticated treatment of the neutrinos, which is the next step to doing full Boltzmann transport to neutrinos, really. And I find the same relationship that 2D blows up before 3D. And this agrees with some three-dimensional GR simulations that use the same leakage scheme. The results are quite similar. So here's that movie one more time. So now with a little more background, you can really drink it in. Again, the purple thing is the neutron star. This is very early, right after the core has bounced and launched this shock. So it's still all very spherically symmetric. And the shock moves out. You get pretty strong early convection behind the shock. And it keeps going, but it fails. So this is a dud. This core collapse does not explode. And once the convection dies down and the shock recedes, this is the standing accretion shock instability. And it sloshes around. And its preferred mode is L equals 1. But you also get in 3D this sloshing, which is really just the superposition of two out-of-phase L equals 1 modes of the standing accretion shock instability. So I find that 3D is harder to explode than 2D. While I'm running these simulations, a paper from the German group comes out that does full neutrino transport, super sophisticated stuff. This one simulation cost 100 million CPU hours. One simulation. Neutrino transport is hard. 3D doesn't explode, but the 2D one does, confirming, I think, my arguments. So that's all I want to say about my science stuff. Are there any questions about science stuff and what I've been doing with extreme computing in the sort of domain science that I work in. So that's science. So the long and the short of it is what my results are saying is that we're probably missing physics in these things. They don't explode in 3D. They don't like to explode in 3D. It's very tough. This is still an open problem. It's not solved. So we're probably missing physics. But there's a lot of physics that we're ignoring in these calculations, like rotation of the progenitor, magnetic fields, and there are some very important magnetorotational effects that can occur that we're looking at right now. But also, we don't have realistic three-dimensional progenitor structures. We're using these 1D models that have all of these fixes for things like convection and turbulence in the evolution of the stars. And I know that we don't have the right initial conditions. And this is a marginal problem. If you start with the wrong initial conditions, you're not going to get the right answer. So this is a big thing. Another thing that we're working on right now is three-dimensional progenitor structures. So I thought then, I'd talk a little bit before showing even more movies about just some things that I've latched onto as key things that I wish maybe someone had told me a couple of years ago or even longer about doing computing at the scale, doing scientific computing. Some of these things you'll find useful, some of them you'll probably think are stupid, but it's my opinion. So for me, high-performance computing is about doing science. That's what I'm interested in, is solving a scientific problem or answering a scientific question with high-performance computing. I'm not a computer scientist. So sometimes that means better is the enemy of good. Someone once told me this. That sometimes the code's good enough, so long as you're getting the right answer. It might not be the best engineered code. It might not be the prettiest code. It might not be the fastest, most efficient code. But if it gets the right answer, that's what matters to me. And someone else told me that never let code optimization slow you down. And what they meant by that is that sometimes it's worth letting a slow code run longer than spending the time optimizing a code so that it runs faster. You'll get to the solution sooner, right? Human time versus computer time. For me, I consider my time a much, much more valuable commodity than a computer's time. And it's all about wall clock time to solution. That's not to say that I shrug off code optimization or work on code. I will tackle it head on, sometimes ignoring my own advice here, because it's about wall clock time to solution. If I think that spending the effort on making the code run faster or run with a smaller memory footprint will get me to the answer that I want quicker than just letting the darn thing run inefficiently, then I'll go for it. This is one that took me a while to learn. I was a print statement debugger for a long time, right? Use tools. We're human, right? grep and print statements are not the only way to debug code, especially really complicated, sophisticated codes that run on extreme scale resources, right? Use GDB or whatever. Valgrind is a great tool. Valgrind has saved my life a couple of times. HPC Toolkit, which is on the Argonne resources, great. Package manager, that's kind of obvious. Use something that highlights syntax. Again, these are duh, right? Use something that highlights the syntax. For me, the most important tool is version control, especially when it comes to code development. You know, I'm sure we're all using version control, right? We're all using version control. Doesn't matter, SVN, Git, Mercurial, you know, this is getting almost as bad as Emacs versus VI. Just so long as you're using some version control system. And it's not just for code. I use it for papers. I use it for the plotting scripts that I use. You know, I stick it in a Git repo or an SVN repo so that I can go back and say, how did I make that plot? Or I can look at the revisions of my papers as I'm moving them through the pipeline. I can hit it with a tag when I submit it. And I say, that's the submitted version, right? And then if I go back and make little edits, oh, I found a mistake after I submitted it, version control tells me, this is the version you submitted, here's the diff. And that makes responding to a referee actually a little bit easier. Here's all the things I changed. Check in early and often. It's like voting in Chicago. Test your code. Test your code. Verification of the code that you're implementing. Verifying, by which I mean, is it doing what you think it's doing? We don't always write code like that. You've got to do that. It's critical. Validation, which means, is your code doing the right thing? That's a harder thing, right? It's also very important, but it's a harder thing. You've got to definitely verify that you're solving the equations you think you're solving. And have a test suite, you know, something that runs automatically every night. It's pointed to your repo. You make some change the you know, whatever day. and it breaks something. You know, test suites are very valuable. They're worth the time to get up and running. Back up your data. This is almost got me a couple of times. Intrepid's file system went down big time last year. Right? It was out for a long time, and there was a lot of data that I hadn't yet moved to tape archive, and I was sweating. I was sweating really bad because I had a paper in the refereeing process based on that data that was sitting there on the disk of Intrepid, and I was sweating. It all came back, though. None of my files were corrupted. But it scared me, and it taught me a very important object lesson. You know, ALCF provides HPSS, right? It's there. Just put your data on it. This needs very little explanation. And a last point, seriously consider making your code open source. You know, I think a lot of times we think that open sourcing code presents a lot of work to the developer, and you say, oh, I don't have time to go through and make it readable. You know, it works for me. I know how to work it. I know how to run it. I don't want to document it. I don't want to have to deal with users, blah, 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 blah. Thing is, you don't have to. You can ignore their emails. But open sourcing your code is analogous to open science, right? What we do is share information. If I were to come up with some new solution to Einstein's equation that helped me solve something about binary neutron stars, and I just wrote a paper and said, I solved this, but see me for the solution. Of course, we don't have any model like this in science for requiring that code that produces the results in a paper be open sourced. Some people talk about this. Some journals talk about this. I don't know that will happen, certainly not in the near term, but we as scientists can choose to do it. And you can also release it under a license that doesn't allow anyone to use it. They can just look at it, right? I think that's a valuable thing. I use an open source code. All of the stuff that I add to the code eventually gets open sourced, released with the code. And it allows people to go and look and see, what exactly did I do? How many times have you read a paper on some piece of simulation or computation and went, what did they really do there? And how did they get around this little spot, right? And it's the kind of thing that you're not even quite sure how to ask the question, but if you could look at the code, you'd figure it out quickly. So I think that's valuable. I want people to do that, right? I've only got one pair of eyeballs to find bugs and mistakes in my code. But open sourcing distributes the debugging in a certain way. And I think much is made about people taking someone else's hard work that is your code and going off and discovering something with it that you might not get the full credit for because you didn't get there first. I don't know how often this really happens. I mean, really. And if it does, so what, right? If you wrote the code, you should have figured out the good stuff to do with it anyways, and did it first.